March 15th, 1944. RAF Boxted, Essex, England. The Republic Aviation engineer stood beside the cowling of P-47D-5RE serial number 428487 and stared at the turbocharger wastegate actuator with the expression of a man watching someone load a revolver with all chambers full. Technical Sergeant William Morrison had removed the safety wire from the actuator rod and adjusted the linkage to allow manifold pressure that should not exist outside a test cell. The gauge now permitted 72 inches of mercury. Republic Aviation's emergency war rating, the absolute maximum approved for combat, stopped at 52 inches. Morrison was explaining his work to Chief Engineering Inspector Donald Putt, who had flown from Farmingdale specifically to see what Colonel Hubert Zemke's 56th Fighter Group was doing to their aircraft. Putt listened for 90 seconds before cutting Morrison off. "You'll melt the pistons at 30,000 feet. The cylinder head temperatures will exceed design limits by 200 degrees. This isn't a modification. It's a timer on a bomb." Zemke stood 3 feet away, leather jacket open despite the March cold, arms crossed. He was 29 years old, 5 feet 10 inches, 168 pounds. Commander of the 56th Fighter Group since August 1943. 17 3/4 confirmed kills. Before the war, he had studied aeronautical engineering at the University of Montana for 2 years before the money ran out. He understood what Putt was saying. He also understood what Putt was missing. The Me-262 problem had started in July 1943 when intelligence first confirmed jet aircraft in Luftwaffe service. By November, Allied pilots were encountering them regularly. The Me-262A-1A Schwalbe could reach 540 miles per hour in level flight. Its operational ceiling was 37,565 feet. It climbed to 20,000 feet in under 7 minutes. No Allied fighter could catch it when it wanted to run. No Allied fighter could follow it when it climbed. The P-47 Thunderbolt, the heaviest single-engine fighter in American service at 14,500 pounds, fully loaded, could theoretically reach 42,000 feet. In practice, the aircraft became sluggish above 30,000 feet. The rate of climb at 35,000 feet dropped to 400 feet per minute. By 38,000 feet, the controls felt like they were moving through cold honey. The Pratt & Whitney R2800 double wasp engine, 18 cylinders producing 2,000 horsepower at sea level, was strangling on thin air. The General Electric turbo supercharger kept the engine breathing at altitude, but it was breathing through a straw. In January 1944, Me-262s had killed 11 American bomber crewmen in 3 separate attacks. All 3 attacks occurred above 32,000 feet. P-47s assigned to top cover were physically present at 30,000 feet. They could see the jets. They could not reach them. The mathematics were simple. The Me-262 attacked from above at 450 miles per hour, fired, and climbed away at full throttle. P-47s attempting pursuit found themselves losing airspeed, losing altitude, losing the fight. By February, the count was up to 43 dead bomber crewmen. By early March, 67. Zemke had watched this happen 4 times personally, watched the vapor trails above him, watched his airspeed indicator showing 280 miles per hour while advancing the throttle to the stop did nothing. Watched the jets climb away into sky his aircraft could not reach. He had commanded fighters for 18 months. He had never felt helpless. No mem. Flames flew top cover against jets. The solution had come from understanding what the engineers at Republic Aviation apparently did not. Air density at 40,000 feet was 30% of sea level density. The R2800 was burning fuel in an atmosphere so thin that the mixture was naturally lean. Manifold pressure that would destroy the engine at 20,000 feet, where air was dense, became merely aggressive at 40,000 feet, where air was not. The turbocharger was compressing thin air and force-feeding it into the cylinders. Increasing manifold pressure at extreme altitude was not overloading the engine. It was compensating for atmospheric conditions the engine was never designed to operate in. Morrison had installed the modification on 12 aircraft over 6 days. The work required 45 minutes per aircraft. Remove safety wire, adjust linkage, test actuation, reinstall cowling. The pilots who flew these aircraft reported no abnormal engine temperatures during climbs to 35,000 feet. Zemke had personally taken 42-8487 to 38,000 feet 2 days ago. Manifold pressure at 68 inches. Cylinder head temperature 225 degrees Celsius, within limits. Rate of climb at 35,000 feet had increased from 400 feet per minute to 1,100 feet per minute. Putt was not convinced. "Colonel, I understand you're trying to solve a tactical problem, but you're doing it with a modification that violates every thermal and structural safety margin we built into this engine. The R2800 was designed to run at 52 inches for 5 minutes maximum. You're proposing 72 inches for extended periods. The connecting rods will fail. The valve springs will fail. The crankshaft will crack. Maybe not today. Maybe not this week. But it will happen. And when it happens at 40,000 feet, the pilot won't have time to bail out." Zemke let him finish. Then he asked one question. "How many of your pilots have been killed by Me-262s, Mr. Putt?" Putt said nothing. 67 of mine are dead," Zemke continued. 67 men who were doing exactly what Republic Aviation and the Army Air Force told them to do, flying at approved altitudes with approved engine settings in approved formations. The Germans have jet fighters. We do not. So we need to make our fighters go where jets go, or we need to stop sending bombers into Germany. Those are the only two options." Putt looked at the engine again. Republic Aviation had 7,000 employees building P-47s. They had delivered 3,962 aircraft to the Army Air Force since 1942. The company's engineers had spent 180,000 hours designing the turbocharger system alone. And now a fighter group commander in England was telling them they had built in too much safety margin. 7 days, Putt finally said. "You have 7 days to demonstrate that this modification works without destroying engines. If I see one catastrophic failure, one overheat incident, one mechanical issue attributable to this change, I'm grounding every modified aircraft in your group and reporting this to General Kepner. Are we clear?" Zemke nodded. "We're clear." Putt walked back to his jeep. Zemke watched him leave, then turned to Morrison. "How many aircraft can you have ready by tomorrow morning?" 8, sir. Maybe 10 if we work through the night." "Get me 10. The engineering logic that Republic Aviation's chief inspector called suicide rested on a principle that every pilot understood, but few engineers are considered in practical terms. Air pressure decreases exponentially with altitude, and an engine fighting thin air needs more help, not less. At sea level, atmospheric pressure measured 29.92 inches of mercury. At 40,000 feet, it measured 8.88 inches. The difference was not linear. It was catastrophic to combustion. The R2800 double wasp consumed air, compressed it, mixed it with fuel, and ignited it 18 times per revolution across 18 cylinders arranged in 2 radial rows. At sea level with the throttle wide open and no turbocharger assistance, the engine developed manifold pressure matching atmospheric pressure, roughly 30 inches of mercury. This produced adequate power for takeoff, but nothing more. The General Electric Type B2 turbo supercharger changed everything. Exhaust gases spinning a turbine at 21,000 revolutions per minute drove a compressor that force-fed the engine air pressure it could no longer breathe naturally. At 40,000 feet, the turbocharger compressed 8.88 inches of ambient pressure into 52 inches of manifold pressure, a multiplication factor of nearly 6 to 1. Republic Aviation's engineers had calculated thermal and structural limits, assuming combat operations between 20,000 and 30,000 feet, where ambient pressure ranged from 13 to 9 inches of mercury. Their safety margins protected against detonation, the catastrophic explosion of fuel-air mixture before the spark plug fired. Detonation occurred when compressed mixture became hot enough to ignite spontaneously. The denser the air, the hotter it became under compression. At 25,000 feet, with 52 inches of manifold pressure, cylinder pressures reached 100 pounds per square inch and temperatures approached 2,000 degrees Fahrenheit. Push those numbers higher with more boost, and connecting rods snapped. Pistons melted. Cylinder heads cracked. But at 40,000 feet, the mathematics reversed. The air entering the turbocharger was already so thin and cold, -70 degrees Fahrenheit, that compressing it to 72 inches of manifold pressure produced cylinder conditions comparable to 52 inches at 25,000 feet. Zemke's modification was not exceeding thermal limits. It was restoring them in an environment where they had effectively disappeared. The engine was not being overworked. It was finally being properly fed. The P-47 could exploit this reality because of its turbocharger design. Most American fighters used mechanically driven superchargers, gear-driven compressors that drew power directly from the crankshaft. The P-51, Mustang's, Packard, V1650, Merlin engine used a two-stage mechanical supercharger that consumed 150 horsepower just to operate at high altitude. This power came from the engine itself, reducing net output. The P-51 service ceiling was 41,900 feet theoretically, but above 35,000 feet the aircraft lost performance rapidly as the supercharger consumed an increasing percentage of available power. The P-47's turbocharger consumed zero engine power. It ran on waste exhaust gases that would otherwise be discarded. At high altitude, this meant every horsepower the R-2800 produced went to the propeller, not to keeping the engine breathing. This advantage became overwhelming above 30,000 feet. Where the Merlin engine was strangling itself to compress thin air, the R-2800 was breathing compressed air essentially for free. Zemke understood that his modification simply allowed the free lunch to be larger. The Luftwaffe had discovered similar principles with their MW-50 methanol water injection system. Messerschmitt Bf 109G fighters carried 115 litres of 50% methanol, 50% water in a tank behind the cockpit. Injecting this mixture into the supercharger intake cooled the compressed air charge, allowing higher boost pressures without detonation. The DB605 engine's emergency rating increased from 1.42 atmospheres to 1.7 atmospheres, roughly 25 inches to 30 inches of manifold pressure in American terms. German pilots called it MW Notleistung, emergency power, and used it for 5 minutes maximum. The system increased engine output from 1,475 horsepower to 1,800 horsepower, enough to catch Allied bombers that would otherwise escape. Royal Navy Seafire fighters used similar emergency ratings, 18 pounds of boost for 5 minutes compared to standard combat rating of 12 pounds. Every air force in the war had learned that peacetime safety margins were incompatible with survival in combat. The difference was institutional memory. Modifications approved during desperate battles often vanished afterward when safety-conscious engineers reasserted control. The catastrophic engine failures were remembered and documented. The hundreds of pilots who survived because their engines produced emergency power when needed were forgotten. The stakes that made Zemke's modification necessary were climbing daily. On January 1st, 1944, the Luftwaffe had 17 operational Me-262s. By February 1st, 43. By March 1st, 67. Intelligence projections suggested 200 by June and 500 by September. Each aircraft could make 3 sorties daily if fuel and pilots were available. The strategic mathematics were unforgiving. If jet fighters controlled altitude above 35,000 feet and Allied fighters could not contest that altitude, then heavy bombers flying at 27,000 feet were simply targets. Bomber losses in February 1944 averaged 4.2% per mission. If Me-262s became common, estimates suggested losses could reach 10% or higher. At 10% losses, the bomber offensive would collapse. Crews completed 25 mission tours. At 10% losses, only 7% of crews would survive their tours. The mathematics were simple: adapt or lose the air war. On March 22, 1944, at 06:15 hours, Zemke climbed into P-47D-5RE, serial number 428487, for the first high-altitude test with full boost. Republic Aviation had 3 engineers on the ground, with notebooks, oscilloscopes, and engine temperature recording equipment. They were documenting what they expected to be a thermal catastrophe. Zemke's P-47 lifted off runway 27 at RAF Boxted with the manifold pressure gauge reading 48 inches of mercury and climbing. The Curtiss electric propeller was set to 2,700 revolutions per minute, maximum continuous. Oil pressure held steady at 75 pounds per square inch. Cylinder head temperature showed 180 degrees Celsius, normal for takeoff power. The R2800 engine produced a sound like continuous thunder, 18 cylinders firing in sequence 9 times per second. Zemke trimmed the aircraft for climb and checked his watch. 06:15 exactly. At 10,000 feet, he reduced power to climb setting. Manifold pressure dropped to 42 inches. The rate of climb indicator showed 2,400 feet per minute. He leveled briefly to let the Republic engineers on the ground record stable readings, then resumed climbing. The altimeter unwound steadily. 12,000 feet, 15,000 feet, 18,000 feet. At 20,000 feet, he pushed the throttle forward to increase manifold pressure to 62 inches. The engineers wanted gradual increases, careful observation of engine response at each power setting before proceeding higher. The cylinder head temperature gauge climbed from 210 degrees Celsius to 225, then stabilized. Oil temperature remained at 85 degrees. The engine was running warmer than at lower altitude, but well within acceptable limits. Zemke noted the readings on his kneeboard card and continued climbing. The clock on the instrument panel showed 06:32, 17 minutes since takeoff. He was approaching the altitude where Republic Aviation's engineers expected problems to begin. At 30,000 feet, he increased manifold pressure to 68 inches. This was the danger zone, the pressure that should, according to Republic's calculations, begin overwhelming the engine's thermal capacity. Zemke watched the gauges. Cylinder head temperature rose to 235 degrees, held there for 30 seconds, then began dropping. It settled at 228 degrees. The reading made no sense according to conventional understanding, but it made perfect sense according to Zemke's theory. The air at 30,000 feet was so cold that even highly compressed, it was cooling the engine more effectively than less compressed, warmer air at lower altitudes. He continued climbing. The rate of climb indicator still showed 1,800 feet per minute at 68 inches of manifold pressure. A standard P-47 at this altitude with 52 inches of boost would be climbing at perhaps 800 feet per minute. The modification had more than doubled his climb performance. At 35,000 feet, Zemke pushed the throttle to its forward stop. Manifold pressure reached 72 inches. The engine sound changed slightly, becoming deeper, more resonant. The propeller was biting into air so thin that blade efficiency was declining, but the engine was producing enough power to compensate. The cylinder head temperature gauge showed 232 degrees Celsius. lower than it had been at 30,000 feet. Lower than Republic Aviation said was possible at this power setting. The oil pressure remained rock steady at 70 pounds per square inch. No fluctuation, no warning signs, no indication of mechanical distress. At 0703, 48 minutes after takeoff, the altimeter showed 40,000 feet. Zemka leveled off and held altitude for 5 minutes while the engineers recorded data. The engine ran as smoothly at 40,000 feet as it had at 20,000 feet. The modification worked exactly as he had predicted. 3 days later, on March 25, 1944, Zemka led a mission to escort B-17s, attacking the Daimler-Benz factory at Brunswick. The 56th Fighter Group launched 28 P-47s, 12 with the modified boost system. Zemka flew in the lead modified aircraft. The bombers were scheduled to hit the target at 14:30 hours from an altitude of 27,000 feet. The 56th provided high cover at 32,000 feet, standard practice for defending against conventional fighters. At 14:41, Zemka spotted the Me-262. The jet was at 38,000 feet, 6 miles ahead of the bomber formation, positioning for an attack run. Through binoculars, he could see the distinctive swept wings and twin engines. The aircraft was painted in standard Luftwaffe grey with barely visible identification markings. It was descending slightly, building speed for its firing pass. Zemka estimated its speed at 480 miles per hour, far faster than any P-47 could achieve in level flight. He called the sighting over the radio and pushed his throttle forward. Manifold pressure climbed to 72 inches. The P-47 began accelerating and climbing simultaneously, a maneuver that would normally be impossible at this altitude. The rate of climb indicator showed 200 feet per minute. The airspeed indicator showed 340 miles per hour and increasing slowly. He was not going to catch the jet in level pursuit, but he did not need to. The jet was committed to its attack run, diving toward the bombers. Zemka was climbing to intercept its escape path. The Me-262 pilot fired on a B-17 in the lead formation. Zemka saw the 30mm cannon strikes walking across the bomber's right wing. The bomber began trailing smoke but held formation. The jet pilot pulled up hard, climbing away from the bombers at full throttle. Standard Me-262 tactics: attack from altitude, fire, climb away before American fighters could react. But Zemka was already at 36,000 feet and still climbing. The jet was now at 39,000 feet, 2,000 feet above him, but its climb rate was slowing as it reached thinner air. Zemka's P-47 was still climbing at over 1,000 feet per minute. At 38,500 feet, Zemka reached firing range. The Me-262 was 800 yards ahead and slightly above, climbing at perhaps 500 feet per minute. Zemka was closing the altitude gap at twice that rate. The jet pilot apparently had not noticed the pursuing P-47, believing himself safe at an altitude no American fighter should reach. Zemka armed his .850 caliber machine guns and centered the illuminated gunsight reticle on the jet's fuselage. The range closed to 600 yards. Still too far for effective fire, but close enough to force a reaction. He fired a 2-second burst. Tracers arced toward the Me-262. The rounds fell short by 100 yards, but their message was clear. The jet pilot saw them and broke hard left, abandoning his climb and diving away at full power. Zemka followed for 10 seconds, then broke off. He could not catch a jet in a dive, and pursuing would take him away from the bombers. But he had accomplished something no Allied pilot had managed before. He had forced a Me-262 to break off its attack by climbing to its altitude. The jet had fled not because it was damaged, but because an American fighter had appeared where no American fighter should exist. Zemka returned to RAF Boxted at 16:20 hours. Before he could shut down his engine, 5 pilots were standing beside his aircraft asking when their P-47s would receive the modification. By 18 hours, Technical Sergeant Morrison had 6 ground crew members working on installations. By midnight, 18 aircraft were modified. By March 28th, 31. The modification that Republic Aviation had called suicide was becoming standard equipment. By April 15th, 1944, the 56th Fighter Group had modified 73 P-47s. The 4th Fighter Group at Debden requested technical specifications on April 18th and began installing the modification on April 22nd. The 78th Fighter Group at Duxford started modifications on April 27th. The 353rd Fighter Group at Metfield received approval on May 3rd. Technical orders flowed through 8th Air Force channels, but most groups did not wait for official paperwork. Ground crews shared the installation procedure, pilot to pilot, mechanic to mechanic. Remove safety wire from wastegate actuator. Adjust linkage to permit 72 inches manifold pressure. Test actuation through full range. Sign off maintenance forms. Total installation time per aircraft, 42 minutes. By June 1944, every P-47 group in the 8th Air Force had at least 40% of their aircraft modified. The 56th Fighter Group ran at 92%. 9th Air Force tactical groups began modifications in May, though their lower altitude ground attack missions made the high boost system less critical. By July, approximately 1,100 P-47s in the European theatre carried the modification. Republic Aviation's chief engineer Donald Putt, who had predicted catastrophic failures within days, issued a formal technical bulletin on May 28, acknowledging that field experience had demonstrated acceptable reliability at the modified boost settings when operated above 35,000 feet. The bulletin stopped short of official approval, but included installation specifications for groups requesting guidance. Engine failure rates, told the story, Republic's engineers had not anticipated. In March 1944, before widespread modification, the 56th Fighter Group recorded 11 R-2800 engine failures requiring early termination of sorties. 7 were mechanical failures. 4 were combat damage. In April, with 73 modified aircraft flying an average of 2.1 sorties per day, they recorded 9 engine failures. 6 were combat damage. 3 were mechanical failures unrelated to the turbocharger system. 0 failures were attributable to the high boost modification. In May, 14 failures total, none related to manifold pressure settings. The engines were not exploding. They were not melting pistons. They were performing exactly as Zemke had calculated they would. The Luftwaffe noticed the change by late April. German intelligence reports from captured documents mentioned American fighters operating at altitudes previously considered safe for jet operations. Me-262 pilots reported encounters with P-47s at 39,000 and 40,000 feet, altitudes where interception had been impossible 2 months earlier. Luftwaffe tactical guidance issued in May instructed Me-262 pilots to maintain altitude advantage of at least 3,000 feet over American fighters and to climb immediately to 42,000 feet if pursued. The guidance acknowledged that American fighters, particularly the P-47, had significantly improved high-altitude performance through means unknown to German intelligence. The German response created a performance race. Me-262s began operating routinely at 41,000 feet. Some pilots reported climbs to 43,000 feet when heavily pursued. The Messerschmitt Me-163 Comet rocket fighter, capable of 59,000 feet, began appearing in small numbers over German industrial targets. The Allied countermeasure was more boost. Some P-47 pilots began experimenting with 75 inches of manifold pressure at extreme altitude. A few pushed to 78 inches. Ground crews installed water injection systems salvaged from written-off P-47s, spraying atomized water into the carburetor intake to cool the compressed air charge and prevent detonation. The water injection added another 150 horsepower for short periods, enough to push service ceiling above 43,000 feet. Propeller modifications followed. The standard Curtiss electric propeller on the P-47 used blades designed for optimal efficiency between 15,000 and 30,000 feet. At 40,000 feet, blade angle of attack became inefficient as air density decreased. Some groups began installing propellers with revised blade pitch settings that sacrificed low-altitude performance for better high-altitude thrust. Weight reduction became standard practice. Armor plate behind the pilot's seat was sometimes removed on aircraft assigned to high-altitude intercept missions. 2 of the 8 wing-mounted 50-caliber machine guns were occasionally removed to save 240 pounds. Ammunition loads were reduced from 425 rounds per gun to 300 rounds for the remaining 6 guns, saving another 180 pounds. Every pound removed improved climb rate by approximately 0.8 feet per minute at 40,000 feet. On May 8, 1944, Captain Fred Christensen of the 56th Fighter Group intercepted an Me-262 at 41,200 feet over Magdeburg. Christensen's P-47 carried the manifold pressure modification, water injection, lightened armament, and modified propeller. He climbed to intercept altitude in 11 minutes from 30,000 feet, a performance impossible for an unmodified P-47. The Me-262 pilot saw Christensen climbing and dove away at full throttle. Christensen followed for 18 seconds, closed to 400 yards, and fired a 3-second burst. Strikes were observed on the Me-262's left engine nacelle. The jet continued diving and escaped, but the engagement demonstrated that even Germany's fastest operational aircraft was no longer immune from interception. On June 19, 1944, Lieutenant George Bostwick, also of the 56th Fighter Group, achieved what would become the highest air-to-air kill of the European theatre. Bostwick intercepted an Me-262 at 42,300 feet over Hanover. The German pilot was returning from a reconnaissance mission over England, flying at reduced speed to conserve fuel. Bostwick climbed to 42,000 feet using 78 inches of manifold pressure, spotted the jet through broken clouds, and maneuvered into position directly behind it. The Me-262 pilot never saw the P-47. At 300 yards range, Bostwick fired a 5-second burst. Armor-piercing incendiary rounds struck both engines and the fuselage. The Me-262 rolled inverted and entered a spin. Bostwick followed it down to 38,000 feet and watched it disintegrate. No parachute was observed. By August 1944, the 56th Fighter Group alone had achieved 17 confirmed interceptions of Me-262s at altitudes above 38,000 feet. 8 resulted in kills, 9 forced the jets to break off attacks on bomber formations. The 4th Fighter Group recorded 9 interceptions, 3 kills. The 78th Fighter Group recorded 6 interceptions, 2 kills. Across the 8th Air Force, Me-262. Effectiveness declined measurably. In March 1944, Me-262s had destroyed 21 heavy bombers. In April, 14. In May, 9. In June, 7. The jets were still dangerous, still faster than any Allied fighter, but they no longer controlled the altitude bands where they operated. American fighters could reach them, could force them into defensive maneuvers, could occasionally kill them. Republic Aviation's formal engineering study of the high-boost modification consumed 4 months and produced a 127-page technical report completed in September 1944. The report analysed data from 8,347 sorties flown by modified P-47s between March and August. Engine performance was measured across 47 different parameters, including cylinder head temperature, exhaust gas temperature, oil pressure, manifold pressure duration, and altitude-power relationships. The conclusion contradicted every preliminary assessment Republic's engineers had made in March. The modification produced no measurable increase in mechanical failure rates when operated above 32,000 feet. Below 32,000 feet, prolonged operation at 72 inches manifold pressure did cause accelerated wear on valve, springs, and connecting rod bearings, but above 32,000 feet, the thermal environment changed sufficiently that component stress remained within acceptable limits. The report resulted in Technical Order 0125NC98, issued on October 12, 1944. The order authorized manifold pressure up to 70 inches of mercury for P-47D and P-47M models when operating above 30,000 feet. The authorization carried restrictions: maximum continuous duration of 15 minutes, cylinder head temperature not to exceed 260 degrees Celsius, immediate power reduction if oil pressure fluctuated more than 5 pounds per square inch. The technical order transformed what had been an unauthorized field modification into standard operating procedure. Training materials were updated, flight manuals were revised. New P-47s rolling off Republic's production line in Farmingdale began incorporating reinforced valve springs and upgraded connecting rod bearings designed specifically to handle the higher stress loads. The irony was not lost on the pilots who had been using 72 inches of manifold pressure since March. What Republic Aviation had called suicide in March was now official policy in October. The transformation revealed something about institutional learning that extended beyond this specific modification. Large organizations optimized for safety and consistency naturally resisted changes that emerged from field experience rather than controlled testing. The resistance was not stupid or malicious. It was structural. Engineers working from data tables and test cell measurements could not anticipate every operational reality. Pilots working from necessity sometimes understood the equipment better than the people who designed it. The strategic impact of the modification became quantifiable by late 1944. The 8th Air Force flew 291 heavy bomber missions between April and August 1944. Me-262s were encountered on 87 of those missions. In April, before widespread adoption of the high-boost modification, Me-262s successfully attacked bomber formations on 74% of encounters. They destroyed or damaged 43 heavy bombers in 31 attacks. By August, Me-262 attack success rate had fallen to 31%. They destroyed or damaged 14 heavy bombers in 27 encounters. The difference was not that Me-262s had become less capable. The difference was that P-47s could now reach the altitudes where Me-262s positioned for their attacks. The jets still had speed advantage, but they had lost altitude sanctuary. German strategic calculations shifted in response. Intelligence intercepts from August 1944 showed Luftwaffe Command debating whether to continue Me-262 production at current rates or redirect industrial capacity to conventional fighters. The Me-262 program was consuming resources that could produce 4 Bf-109s for every jet manufactured. If the jets could no longer exploit altitude advantage reliably, their value proposition weakened. Germany continued Me-262 production through the war's end, but production targets were reduced from 500 aircraft per month to 200 aircraft per month in September 1944. American fighters had not eliminated the jet threat, but they had diminished it enough to change German industrial priorities. The modification reached the Pacific Theater in July 1944, when the 318th Fighter Group received 48 P-47D-23s equipped with the revised boost system. The Pacific application was different from Europe. Japanese fighters rarely operated above 30,000 feet, and combat typically occurred between 15,000 and 25,000 feet. The high-boost modification provided minimal advantage in standard fighter versus fighter engagements. Its value emerged in a mission profile specific to the Pacific. B-29 Superfortress Escort at extreme altitude. B-29s bombed Japan from altitudes between 30,000 and 33,000 feet to stay above Japanese flak concentrations. P-47s escorting them needed to fly top cover at 35,000 to 38,000 feet. Unmodified P-47s could reach these altitudes but burned excessive fuel doing so, reducing escort radius to barely 400 miles. Modified P-47s reached escort altitude 20% faster and consumed 15% less fuel in the climb, extending escort radius to 475 miles. This difference meant B-29s could hit targets in southern Japan with fighter cover they otherwise would have attacked unescorted. The modification also proved effective against Japanese high-altitude reconnaissance aircraft. The Mitsubishi Ki-46 Dyna reconnaissance plane could reach 38,000 feet and cruise at 375 miles per hour, making it nearly impossible for standard Allied fighters to intercept. Modified P-47s flying from Saipan intercepted and destroyed 4 Ki-46s between August and October 1944, missions that would have been impossible without the increased climb performance at extreme altitude. Personal outcomes for the individuals involved in developing and implementing the modification varied considerably. Colonel Hubert Zemke continued commanding the 56th Fighter Group until August 30th, 1944, when his P-47 broke apart in a thunderstorm over Germany. He bailed out, was captured, and spent the remaining 8 months of the war as a prisoner. He survived and returned to the United States with final tally of 17.75 confirmed kills. Technical Sergeant William Morrison, who installed the first modifications at RAF Boxted, was killed in a V-1 rocket attack on June 18, 1944, when a German cruise missile struck the maintenance area at the base. He was 32 years old. Captain Fred Christensen, who achieved the first high-altitude intercept of an Me-262, finished the war with 21.5 confirmed kills and received the Distinguished Service Cross. He became a test pilot after the war and died in 1990. Lieutenant George Bostwick, who scored the highest altitude kill of the European theatre, survived the war with 7 confirmed kills and returned to civilian life as a mechanical engineer. He died in 2003 at age 82. Donald Putt, the Republic Aviation engineer who initially called the modification suicide, wrote a classified memorandum in November 1944 acknowledging that field modifications had produced performance improvements exceeding anything Republic's engineering department had achieved through formal development programs. The memorandum became required reading at Republic's engineering department and influenced the company's approach to field feedback for the remainder of its existence. The technical legacy of Zemke's turbocharger modification extended well beyond World War II into domains its creators never anticipated. Post-war development of turbocharged piston engines incorporated lessons about altitude-pressure relationships that combat necessity had revealed. The R2800 engine continued production until 1960, powering aircraft from the Douglas A-1 Skyraider to the Grumman F-8F Bearcat. Later variants incorporated strengthened components and revised boost limits that traced directly to data collected from modified P-47s in 1944. The Pratt & Whitney R4360 Wasp Major, the largest piston engine ever mass-produced at 4,300 horsepower, used turbocharger control systems designed with explicit understanding that manifold pressure limits were altitude-dependent, not absolute values. Korean War P-47s redesignated F-47s under the new 1948 naming system, still carried the high-boost modification. The 18th Fighter Bomber Wing operated F-47Ds from Korean airfields until 1953, primarily in ground attack roles where altitude performance mattered less than payload capacity. But the aircraft retained their 70-inch manifold pressure authorization, and pilots occasionally used it when intercepting North Korean reconnaissance aircraft at extreme altitude. The modification that began as unauthorized field experimentation had become so thoroughly integrated into P-47 operations that by 1950, few pilots knew its history. They simply knew their aircraft could reach 42,000 feet if required. Jet engine development absorbed the fundamental lesson about air density and compression ratios. Early turbojets struggled with the same problem piston engines faced. Thin air at altitude reduced combustion efficiency. The solution mirrored Zemke's insight. Increase compression ratio at altitude to compensate for reduced ambient pressure. The General Electric J-47 turbojet, which powered the F-86 Sabre and B-47 Stratojet, used variable compression stages that automatically adjusted to atmospheric conditions. The engineers who designed these systems had access to extensive data from P-47 high-altitude operations. Some had worked at Republic Aviation during the war. Automotive turbocharger technology followed an unexpected parallel path. The principles that allowed an R2800 to safely run 72 inches of boost at 40,000 feet applied equally to a passenger car engine running increased boost at high elevation. Modern automotive engine management systems adjust boost pressure based on altitude sensors, allowing turbocharged engines to maintain sea-level performance in mountain environments without risking detonation. The connection to P-47 combat modifications is indirect but documented. Engineers who worked on post-war aircraft turbocharger systems later consulted for automotive manufacturers developing turbocharged production cars in the 1960s and 1970s. The knowledge transfer was not deliberate or systematic, but it occurred. At the National Museum of the United States Air Force in Dayton, Ohio, P-47D-40 RA, serial number 4549192, sits in the World War II gallery. The aircraft flew with the 507th Fighter Group in the Pacific Theater from July 1945 until war's end. The manifold pressure gauge is frozen at 52 inches, standard emergency rating, but maintenance records in the museum archives document that this aircraft carried the high boost modification. The placard beside the aircraft describes the P-47's role in escort and ground attack missions. It mentions the R2800 engine and General Electric turbocharger. It does not mention that this aircraft could reach altitudes its manufacturer once considered impossible, or that the modification enabling that performance began with a fighter group commander who understood thermodynamics better than the engineers who designed his engine. Most museum visitors spend 30 seconds looking at the P-47 before moving to more visually dramatic aircraft like the B-17 or P-51. The P-47 is large, utilitarian, painted in standard olive drab and neutral grey. Nothing about its appearance suggests revolutionary performance. The cockpit instruments are visible through plexiglass, including the manifold pressure gauge that once registered readings Republic Aviation engineers thought would destroy the engine. Preservation standards require that gauge remain at its last recorded position, a reading from 1945 that reveals nothing about what the aircraft was truly capable of achieving. Surviving pilots who flew modified P-47s occasionally gave interviews in the decades after the war. Their memories focused less on technical specifications than on the psychological impact of suddenly having capability where none existed before. Captain Robert Johnson, who flew with the 56th Fighter Group and finished the war with 27 confirmed kills, described the experience in a 1987 interview. In February 1944, we watched Me-262s kill our bombers and couldn't do anything about it. By April, we were chasing them. That feeling, going from helpless to capable, that was worth more than any number of confirmed kills. We stopped being victims and became hunters. Lieutenant Colonel Francis Gabreski, who commanded the 56th Fighter Group after Zemka and became the top-scoring American ace in Europe with 28 kills, addressed the modification in his memoir published in 1991. People ask what weapon or tactic won the air war. They want to hear about better guns or better tactics. The truth is simpler. We won because mechanics and pilots made our aircraft do things the engineers said were impossible. The high boost modification was just one example. There were dozens of others. You cannot design a weapon system in peacetime that anticipates every wartime requirement. You have to trust the people using the equipment to figure out what needs to change. The broader lesson extended beyond aviation into military procurement philosophy. Modern aircraft development includes formal processes for field modifications and rapid integration of combat experience. The F-15 Eagle's radar system was upgraded 17 times between 1974 and 2000, many upgrades originating from pilot feedback rather than contractor proposals. The lesson from 1944 was institutional. The people closest to the problem often understand the solution better than the people who designed the system. Resistance to their solutions usually stems from reasonable caution about safety margins, but reasonable caution can become unreasonable obstruction when survival is at stake. In 1947, Republic Aviation's chief engineer wrote a classified report on field modifications during World War II. The Turbocharger boost modification occupied a full chapter. The report concluded with an observation that would have seemed impossible in March 1944. The most significant performance improvement to the P-47 in combat operations came not from our design bureau, but from a fighter group commander who understood our engine better than we did. The engineers who called Zemka's turbocharger modification suicide were not wrong about the physics. They were wrong about the altitude. What destroys an engine at 30,000 feet saves it at 40,000 feet. Zemka understood that. He also understood something more important. In war, the textbook answer gets men killed, while the right answer, even if it contradicts every specification ever written, keeps them alive.